All right, let's just jump right into it. Welcome to today's Explainer, where we're going to unpack this totally invisible, high-stakes battleground that's happening deep inside every modern electric vehicle. We're talking about the EV's internal communications, specifically the Controller Area Network, or CAN bus. Now, if you're into EV architecture, you already know the motor controller and the vehicle controller are constantly talking to each other. It's basically the vehicle's central nervous system. But what actually happens when that chatter just drops? The engineering life cycle required to prevent a catastrophic loss of communication here is honestly nothing short of heroic. So today we're exploring the deep technical specs and those invisible safety shields that keep these vehicles on the road, and more importantly, keep you safe when the electrical environment goes absolutely haywire.
So here's our game plan for this explainer. First, we'll look at the root causes of failure, then how software and hardware team up for a collaborative defense. We'll hit DFMEA, key design prevention, move on to PFMEA, strict process controls on the manufacturing floor, and finally wrap up with DVPNR, which is essentially a production validation torture chamber.
To set the stage, let's ask a genuinely terrifying question. What actually happens when an EV's brain stops talking to its muscles at high speed? Imagine you're cruising down the highway, your dual motor controller is pushing massive power, and suddenly those lightning-fast CAN or CAN-FD messages from the vehicle controller just vanish. They get lost in the noise or they time out. Without an immediate, highly controlled response from the system, the vehicle could lose stability, throwing you into a spin or, honestly, much worse. It's not just a glitch, it is a critical control failure. And because the stakes are literally life and death, this entire communication system operates under the ultimate automotive safety standard, ASIL D. This standard is completely merciless. It dictates a fault-tolerant time interval, or FTTI, of strictly less than 100 milliseconds. But to be safe, engineers actually set the communication timeout threshold even tighter, usually right at 50 milliseconds. The system has exactly that long, a fraction of a blink of an eye, to realize it's gone blind, catch the error, and gracefully bring the motor power and torque down to a safe state without causing a crash.
Okay, part 1, root causes of failure. Because, before we can build an impenetrable shield, we really need to understand the microscopic villains trying to crash the car's network in the first place. The source material actually breaks this down into 4 specific threats, and it's basically a war on 4 fronts. First, electromagnetic interference, or EMI coupling. Second, this fascinating mechanical issue called pin fretting corrosion. Third, on the software side, task priority inversion. And fourth, low voltage power sag. Just think about this environment for a second. You've got high-frequency vibrations from 100 to 1000 Hz shaking the connectors, plus crazy thermal shocks from -40 to 125 degrees Celsius. All of this causes the connector pins to physically slip against each other by just 10 to 100 micrometers. That tiny micro-friction scrapes off the metal, builds up insulating oxidation, and boom, you get microsecond physical disconnects. Add in a 12-volt battery drop during heavy loads that starves the CAN transceiver, or an OS latency where a MAF task hogs the CPU and delays communication. It's just a brutal environment.
But the single most violent threat is right here, 10 kilovolts per microsecond. That is the sheer switching speed of the high-voltage silicon carbide MOSFETs. They switch so unbelievably fast that the voltage spikes inject massive common mode noise directly into the low-voltage communication lines. If that noise turns into differential interference, it scrambles the CAN logic. It essentially creates a digital traffic jam of continuous bit-stuffing errors. And if those error counters hit the 255 threshold, the controller is forced into a bus-off state, literally severing communication entirely.
Which brings us to part 2, software and hardware collaborative defense. How exactly do we catch these errors before the car loses control?
The secret sauce here is a brilliant dual-core redundancy. Think of it like a pilot and a co-pilot. You've got the doer core, that's the main processor, actively unpacking CAN messages and updating the torque instructions. But right next to it, totally independent, is the checker core. This co-pilot runs a strict watchdog timer, constantly monitoring the timestamps of incoming messages. If the checker sees that the instruction interval has dragged past 50 milliseconds, it assumes the main core is locked up, flying blind, or compromised. The checker instantly steps in, interrupts the main core, and completely takes over the safety control path. And what happens next is absolutely crucial. When that 50 millisecond timeout hits, the system can't just violently yank the power. A hard torque cut at 70 miles an hour would basically lock the wheels and cause a massive wreck. Instead, it triggers a smooth, graceful degradation. The torque is seamlessly ramped down at a precise rate of 1,000 Newton-meters per second. Once it safely drops below 5 Newton-meters, the system locks out the gate signals and enters what's called an active open circuit or AOC state, so instead of violently halting, you just smoothly glide to safety.
moving on to part 3, key design prevention, or the DFMEA side of things. Because as cool as catching a failure is, preventing it at the engineering level is way better.
To block all that extreme radio frequency interference before it even starts, engineers mandate automotive-grade digital isolation chips with a common mode transient immunity, CMTI, of over 100 kilovolts per microsecond. And they don't use standard termination, they use a split termination design, which acts like a specialized electrical shock absorber. It uses two incredibly precise 60-ohm resistors tied to a high-grade ceramic ground capacitor. Paired with common mode chokes, it creates an ultra-low impedance path that just violently suppresses electromagnetic noise right at the physical layer. Add a synchronized main clock source so temperature swings don't mess with baud rates, and you've basically built an impenetrable shield.
Then there's the golden physical routing rule, 150 millimeters. The low-voltage CAN wires, which, by the way, have to be twisted at least 33 times per meter, must maintain a strict physical distance of at least 150 millimeters away from the high-voltage bus bars. I mean, space is a massive premium in an EV, but this air gap is absolutely non-negotiable to prevent near-field electromagnetic crosstalk.
All right, part 4, strict process control. This is the PFMEA stuff. Because look, you can design the most perfect board in the world, but if it's built poorly on the manufacturing floor, it's still going to fail. The process control here is literally zero tolerance. For surface mount soldering of these critical CAN components, the production line uses 100% 3D X-ray or ultrasonic inspection. The absolute max allowable voiding rate in the solder is just 5%, with no single void larger than 1%. Why so strict? Because if there's even a tiny air bubble in that solder, all that thermal and vibrational stress we talked about will eventually crack it wide open while you're driving. Even the wire harnessing has these crazy automated safety nets. When they crimp the pins onto the communication cables, they use closed-loop servo machines doing real-time force displacement monitoring. If the machine senses that a crimp is even a fraction of a millimeter off tolerance, it instantly locks the fixture. The operator can't even remove the bad part without a supervisor. And at the end of the line, they actually inject deliberate faults into the system just to physically verify that the controller triggers the diagnostic code and initiates that torque ramp down in under 50 milliseconds. Finally, part 5, production validation. Before any of this ever goes to market, it has to survive the DVP&R phase. Welcome to the torture chamber. They don't just test these units, they absolutely abuse them. Just look at the first test on this table. They run the motor at 12,000 RPMs under full load, maxing out the switching speeds, and directly inject 200 milliamps of high-frequency interference straight into the lines. The passing grade? 0 frames lost. Not a single one. Then they toss it on a shaker table, applying 3-axis random vibration while cycling temps from -40 to 125 degrees Celsius for over 1,000 hours. The contact resistance can't shift by more than 1.2 milliohms, and they can't log a physical disconnect longer than 1 single microsecond. Lastly, on a hardware-in-the-loop simulator, they cut the CAN signal entirely at full speed. The system has to recognize the fault, throw the code, and smoothly ramp down torque without locking a single wheel, all well inside that 100-millisecond window. Which leads us to a pretty fascinating final thought. With variables this extreme, could dynamic high-frequency electromagnetic simulation be the ultimate key to designing the perfect failsafe? The source material shows engineers are now using Python simulation models to calculate exact transient dynamics, frame conflicts, and safety margins before a physical prototype is even built. It really leaves you in absolute awe of the millions of calculations and perfectly executed tolerances keeping you safe on the road. Definitely something to think about next time you're silently speeding down the highway in an EV. Thanks for hanging out for this explainer, and we'll catch you in the next one.